Okay, so we started a little bit late here, but I think we're just going to go right on in, start with Anki. And yeah, I think we'll just move forward with this. Actually, before we go in, I've been thinking more about like what I'd like to see with the rest of this. So I think I'm going to finish this video, and then now that I have a pretty good conceptual understanding of calculus, I'm then going to dive into like the practical, like, or actually I think what I'll do next, because I think my conceptual understanding for calculus is pretty decent right now. We're about, what, 6 hours in? Yeah, we're about 6 hours in now, working on 7 for learning this. And so my conceptual understanding is pretty good. And so I think the next step would just be to grab a test, an example test online, like a final, preferably, and then start going through every question, like identify the question, what do I not understand about the question, and then solve the question, and just do that for every problem on the exam. And then if I feel confident enough in all of those things and feel I have good understanding of them, maybe I'll take another test for a different course or something like that, or I'll just like check mark it and say that I'm finished. We'll see there, but yeah, I think going through a final exam and ensuring that I understand each one, and this isn't like a surface level understanding. This is not like I look at it and I recognize this thing. Often in learning, people will get confused with recognition and understanding. Like if someone looks through their notes, which is like reviewing through looking through notes, is just an awful way for learning. And the reason being is you're not like really doing any effortful thing. Same thing for highlighting and things like that. And so I'm going to look through and have a deep understanding such that like when presented a variation of the problem, I could complete it. And that would be the goal. And I'm feeling pretty good about this. I've super enjoyed calculus so far. I think it has been a quite exciting thing. And like, yeah, I think it's been great. So I think we will just go ahead and start with Anki, and then we will progress from there. So I'm gonna zoom this in. Okay, here we are, Anki. We only have 5 today. So what's the concept of removable discontinuity? So first we'll define what a discontinuity is within calculus, and then we'll talk about a removable one. So a discontinuity is when there is a whole gap or a break within the outputs of a function. So I guess inputs and outputs. I guess it's more proper to say within a function. So inputs or functions have inputs and outputs. So this would be for a given input like x equals 2, the function would return undefined. It just wouldn't be able to do that. So you'd have all the values above and all the values below, but you wouldn't have that there. And I think I do want to go into the 3 ways that there are discontinuities within functions. I think it was like jump, skip, I don't know what it was. Oh, sorry. The removable portion is the fact that you can remove it if you can factor out, or if you can make an algebraically equivalent function that no longer has that discontinuity. So in a way, you've removed that discontinuity there. Okay. What is the power rule? I think the powerful. Oops, for derivatives in calculus. Okay, so I'm actually going to, okay, I remember this one. So this is where like a really quick way to determine a derivative, if you have a function that enables it, is to take so let's say we have x to the 5, or x to the 5. To take the derivative of that, we would do x to the 4, and then so it'd be 5x I'm gonna write this up. This is not clear to explain. Excalibur, where are you? Okay, so if I have x, f of x equals x to the 5, then that would be f of x equals 5 times x to the 4th, because it's this f of x to the n here is equivalent, or actually no, it's not the equivalent. It's the derivative. The derivative of this can be found by doing f of x equals n x and a minus 1. Okay, so that's correct. What's the difference between the secant and tangent lines? The tangent line represents the slope of a function at an instantaneous point, whereas the secant line, and the instantaneous point meaning it's at one point determining what the slope of the line is, and the secant line determines the average between 2 points, and it passes through two points on the function. Oh yeah, I guess, and the instantaneous slope, it's the same as the derivative. At least the function of that is. What's concepts of continuity? This is unbroken outputs within for a function. Breaks, jumps, or holes. That's the thing I'm looking for. Okay. Breaks, jumps, or holes in a function. What are these? Okay. Yes. Okay, what's the difference between infinite discontinuity and jump discontinuity? Okay, so it looks like I did make some... I do remember this question. An infinite discontinuity, I'm unsure. I think the break discontinuity is when we have undefined. I think a jump discontinuity is when we're like taking like absolute value or something, because that would make you wouldn't get a particular output. It would just... No, that's incorrect. I'm not sure. Okay, an infinite discontinuity when a function's limit approaches infinity at a point. Okay. Okay, approaches infinity. I'm interested why they call it a discontinuity. It approaches infinity. For an infinite discontinuity, why is it called a discontinuity in calculus? I really have to wait a long time for this thing. Function does not approach a finite limit at the point of discontinuity. So it approaches infinity instead of an... Oh, interesting. Okay, so... Interesting. Interesting. So instead of approaching a point... infinite discontinuities approach infinity. So say I have like a limit that would be the discontinuity in an infinite discontinuity. Yeah, say I have the limit for an infinite discontinuity, but there is no I don't know how to describe it now. Let's see. So for a typical, as the number increases, or as we approach the limit, we arrive at a finite number. but for the infinite function, as we increase, we arrive at an infinity. I do have a question regarding. So why is it the case that we call this an infinite discontinuity, right, for something like 1 over x, but we don't call something like a normal function having an infinite discontinuity? Because as my input increases, it approaches as my input increases, I approach an infinity. In both the situation where my f of x equals x, right, or f of x equals 1 over x. Like, both of those are approaching an infinity. But yeah. So yeah. So why is it that? Oh, I don't want to say Could you help me understand a little bit more about this infinite discontinuity? It seems that it is also the case that outputs approach infinity as inputs approach infinity. Period. How is this different than this discontinuity? Okay, where the unbounded behavior occurs. Infinite discontinuity happens at a specific finite x value where the function's outputs tend to... Oh, a specific finite x value. So is it considered an infinite discontinuity because I can never reach 1 in the case where I have 1 over x for a function? Is it the case that infinite discontinuities occur in all functions that, or rather most functions that, or where the variable exists in the denominator? Oh, wait. Oh. So, okay. Yeah, so 1 over x, as x approaches infinity, it goes to 0. Okay, I think I'm gonna... So this seems like typical math, not typical math, but this seems like a... This seems like typical math jargon. Or they say blows up. Are there situations where I have an infinite discontinuity, but it is not because I have 0 in the denominator? Okay. Infinite discontinuities often happen due to denominators approaching zero, but can occur. Okay. So. Oh man. When we have an asymptote, does this occur every time we have an asymptote that would lead us to infinity? Okay, so a vertical asymptote. Though we could have a non-vertical asymptote, say, where our slope is 1, that is still an asymptote, but is not an infinite discontinuity because it doesn't approach infinity. It just merely approaches slope of 1. Okay. I see. Okay, so it seems like I'm still not 100% sure of how this is a discontinuity, because I can understand that, these functions like quickly can blow up, meaning they quickly approach infinity. Like, for example, this right here. So if I had this and then it never crossed this line, it just goes whoop. That's a little bad. Let's see. We'll draw a little better line. We'll say it goes zoop. And then we'll just pretend it never touches that line. So I can understand that it never. Okay, well, actually, let's think. Okay, so, okay. Okay. I think I have an idea for what it is. Okay, so say we have, okay, so say we have two graphs here, and one of them is like a function that does like this number or something like that. And then say we have a function that approaches a vertical asymptote. So I haven't thought about it like this before. We'll say this is the asymptote. And then this is our like little function, zoop, and zoop. Okay. Okay. So I just thought about this. So for typical functions, like this guy, like this portion here approaches infinity, and this portion here approaches infinity. As the inputs approach like positive and negative infinity, respectively. And I guess this one here would also approach negative infinity as my input approaches negative infinity if it does go that way. However, this whole like domain of values here, or maybe it's range, I can't remember if that's the correct terminology, they just don't exist within the function. Because as this approaches infinity, we don't like capture any of these values. And I think probably in most functions, as something approaches infinity, the other thing also approaches approaches infinity. Whereas for the output for this function, we're like approaching like 4 or something like that. Okay. I think I'm feeling pretty good about that. Let's see if validate my idea. Okay, I have an idea of how this might be, period. Could you tell me if it's correct, question mark? So for a given function, maybe x squared, it increases exponentially. However, as my input approaches negative or positive infinity, it's going to do the same for my output, negative or positive infinity, period. For an infinite for a function with an infinite discontinuity, we'll say it has a vertical asymptote, period. In this function, as I'm approaching infinity, in this function, as I'm approaching infinity, I am approaching the asymptote, which would be like 4 or something. Period. So this would mean that there is an entire domain or range, I can't remember what the correct term is, of values that don't exist within the function because of this asymptote. Would this make the function discontinuous, question mark? Okay. Okay. So I think they misunderstood, because I was saying that this is correct. Okay, it is the case though that it's always positive. I'll give them that. Okay, so domain is the input, range is the output. Sure, that would be great. Oh, okay. So, okay. Okay, that makes sense. So I never thought about the fact that for an infinite discontinuity, that like we could have something on this other side. So it makes sense that like we never have 4, even though the functions approach 4. Okay, that makes more sense. I was just thinking about it like in the context of only one of these slices. And for me, like that didn't super make sense. Well, Yeah, because I was thinking that if we go back to my understanding here, I was thinking, oh, maybe it's the case that like for this asymptote, we just don't have all these values, and because we lack these values in our range, then it's discontinuous. However, this domain right here is right. That'd be x. Yeah, the domain at this point is an input that doesn't exist. Okay. I see. So when we are talking about discontinuities, are we talking about only discontinuities within the domain or inputs, or do we also think about, or are the outputs or range also something that is thought about? I don't know. Okay. Fails to be continuous based on its inputs. Okay, this is the best. This is the best like snippet that I've seen. Okay, so it's on inputs. Okay. Could you describe the difference between jump discontinuity and a removal discontinuity? When the left hand limit and right hand limit at a point exist but are not equal. Okay. Okay, I think I understand all of the discontinuities. So an infinite discontinuity is when we don't have, say, x equals 4 within our domain, and the output as x reaches 4 on the input on the negative or the positive side. On the, like, reaching 4 from going from a smaller point to a greater point and from a greater point to a smaller point. That both of those become infinity when we try to reach it, but it does not exist within the domain. A jump domain or jump discontinuity is when we just don't have this value, and it jumps across. So but we just don't connect. So okay, maybe I'll need a little bit more here. Okay, I think I'm just gonna note these, and I'll add these because I'd like to try to finish the video today. Okay, so I'm going to add. Okay, so we will. Okay. Okay, we talked about removable discontinuities, and now we need an infinite discontinuity. In calculus. Okay. Okay. Could you describe what you mean in the jump discontinuity with the left and right limits? Oh, okay. Oh, okay. Right hand limit and left. Okay. What are the concepts of right hand? Okay, so it's describing that right hand and left hand limits are the limits that are found for the domain of values from the left side and the right side. So in the example where we have an asymptote on x equals 4, the left-hand limit is as we're approaching 4 from, like, imagine if we're going from 0 to 4. And the right-hand limit would be if we're approaching, like, positive infinity and we're coming to 4. Okay. Perfect. Okay. So that makes sense. So now I would just like an example of jump discontinuity, because I know what a removable discontinuity is. And what I understand is that a jump discontinuity, or sorry, a removable discontinuity, or rather, yeah, a jump discontinuity is just a non-removable discontinuity. So is a jump discontinuity merely a non-removable discontinuity? Okay. Oh. That's good to know. What makes a discontinuity removable? Because I see. So removable discontinuities is when the left-hand and right-hand limits are equal, but the function are equal. So it's describing here that they're not equal. A discontinuity non-removable in calculus. Plus. Okay. You're good there. Okay, sick. So we will go. Okay. Looking for the question where it asked breaks, jumps, and okay, jumps. So for describing the difference between a break, jump, and hold discontinuity, the break would be a non-removable discontinuity, the jump would be an infinite discontinuity, and the hole would be a removable discontinuity because the hole can be filled. Okay, so jump is not infinite. Okay, so it looks like the jump and break seem to be similar. Or the same thing, maybe. Yeah. So the removable one is the hole. Jumps and breaks are the same, it seems. Okay. Okay, so when we talk about jumps, breaks, and holes, we're not talking about infinite discontinuities. But the difference between a break and a hole is that a hole can be filled by removing the discontinuity. Okay. This is good. This is good. Okay. Let's see. So now I'm just going to capture that difference between a jump and a hole. Break / jump, discontinuity, and a hole, discontinuity. Sweet. Oops. Holes can be removed and jumps cannot. I don't want that bold. Okay. I think we are good in understanding those things. Yeah, I feel like we're getting close to where we just need to start like doing math. So. Okay, I guess I don't know what uniform continuity is, or power series, or the Riemann integrals, or this guy, the higher order derivative, but okay. Okay, so I think I'm going to first finish the video. Looks like we have about 20 minutes left. We probably won't finish tonight. I will be real. And then after that, I think I'm going to maybe go through my cards and just list out, or maybe I could do this off stream, but I'd like a list of all the things that I learned so far. Yeah, I think I'd like that, just to get a visualization. Okay, so let's continue. And for the math portion here, I'm not terribly concerned about pulling out the methods, because since this is just an overview, it's more conceptual than it is practical in terms of like telling me how to do an integral or what have you. So we'll just kind of zip through that portion. Oh, actually, if we're going at 2x speed, we should be able to finish this thing.
So integration is the opposite process of differentiation.
Let's see, we got desktop audio. We do.
So you can call it anti-differentiation. Now I want to take a minute to compare derivatives and anti-derivatives, or integration, side by side. Just so you can see a summary of the key differences between the two. So when dealing with derivatives, you're looking for a function that will tell you the slope of the tangent line.
Okay. I do have one more thing. So one thing I really liked about this section here, I think it's like literally just a couple.
Now when dealing with integration, whereas
right here. So derivatives are about the slope here, x and y, or y over x, and the area is about, the integration is about the area, and so I'm going to note that because that's like a really powerful conceptual idea to understand derivatives and integrals like vastly differently, right? So, okay, so I'm going to have two questions. One will be one that captures just the difference between slope and area. So it'll be how do slope and area relate to calculus terms like integrals and derivatives. Okay. Okay. Okay, represents the slope of a function at a point. Perfect. Okay, and then the next one will be how do these two things, two expressions here, let's see, what is the difference between a function and an expression? Oh, no. What's the difference between a function and an expression? Ah, shoot. In mathematics. I think my my intuition or my understanding to this point is that an expression it doesn't take inputs and outputs. It's merely like a description of some things. So if I have like a description of some things, a description of having some mathematical how should I know how to describe this? It would be an example of it would be 2x plus 3. I think that's an expression because it doesn't evaluate to anything. Okay, maybe a math something that evaluates to something, and it has like variables, coefficients, numbers, combinations that represents a value. It doesn't inherently define. Oh, perfect. Yes, I got it exactly. Okay. Actually, I'm going to note that. Mathematics. HTML. Oh, shoot. That's not what I wanted. Oh, this is fine, actually. Going just to remove that. Okay. I do not care for that. Okay, why are you H2? Oh. You should not. Okay. We're just going to try this again. Here we are. And this one will just be math. Okay, and then we're back. Okay. So now we have what I was going over initially, of which I do not recall. Aha, yes. Okay, it'll be these two. How do these expressions relate to calculus? Maybe I'll just copy the delta symbol. Actually, I will have ChatGPT do this for me. Perfect. Copy. Oh, I need this. What? Oh, I don't want Anki Math Jacks. Why did it do that? Okay, looks like it automatically... No, it does not automatically do that. Okay, maybe it does. So we'll just live with it. Okay. Okay. The only thing I don't like about having it convert to MathJax is I can't copy it out. Oh, okay. So I was trying to get at the fact that we have the slope here. Oh, actually, I do want this. Okay, relate to. Okay. Nice. That is what I was wanting. Okay, yeah. So what I was wanting is there's this big idea here where, or when we're doing an integral, or when we're taking a definite one, we want the area, and when we're doing a derivative, we want the slope. There is one more thing that I want to like touch on, because this, well, actually, it's something I'd like to investigate at some point, because it's like, yeah, I guess I'll probably understand a little bit more when we go into more depth in integrals. It is interesting that like x and y like equal the slope, or sorry, the area, or the relationship when we have the formula there. Yeah. I'd like, well, maybe, I think this is probably too simplified for me, or sorry, not too simplified for me. This representation is too simple for me to, well, I don't know. I think we'll look into this a little bit more, I believe. Okay.
You're dividing the y values by the x values, whereas when you're integrating, you're multiplying the y values by the x values. And multiplication and division, they're opposite processes. And that's essentially what you're doing when you're differentiating and integrating. Now, of course, it's a little bit more complicated than that, but that is the gist of it. Let's consider this problem. So we have a function, a of t, which is 0.01 t squared plus 0.5 t plus 100. And this function represents the amount of water in gallons that is inside a tank at any time t, and t is in minutes. So what we need to do is calculate the amount of water at the following times. So when t is 0, when it's 9, 10, 11, and 20. So go ahead and do that when you get a chance. So feel free to pause the video. And so here is our original function. It's 0.01 t squared.
Okay. So this one will just be inputting the different inputs to get the outputs. I'm not super concerned about this because this is just algebra, and I can do this.
Plus 0.5 t plus 100. So let's go ahead and plug in 0. If we plug in 0, it's going to give us this value, which is 100. Now, if we plug in 9, it's going to give us 105.31. Now let's plug in 10.
So I think I'm going to skip ahead here.
So it's going to be 106. We're going. So let's focus on part when t is equal to 10. We're dealing with. So what is the derivative of t to the 2 minus 1, which is in the power prime of t? So let's begin by finding the first derivative, a prime of t. So what is the derivative of t squared? So using the power rule, it's going to be 2t to the 2 minus 1, which is 2t to the first power, or simply 2t. Now what is the derivative of t, or t to the first power? It's going to be 1t raised to the 1 minus 1, which is 1t to the 0. Anything raised to the 0 power is 1. So this is going to be 0.5 times 1. Now what about the derivative of a constant, like 100? The derivative of any constant is 0. So this is
something interesting.
A prime of t. So what is the derivative?
So we have this function here, and when we're taking the derivative, we're taking the derivative of each component of the function. I guess that. Well, I don't know. I just didn't expect that. I thought it was like, well, yeah. I just didn't expect that. That's surprising to me. Just not what I had imagined.
Derivative of t squared.
Even though I didn't really have a clear conception.
So using the power rule, it's going to be 2t to the 2 minus 1, which is 2t to the first power, or simply 2t. Now what is the derivative of t, or t to the first power? It's going to be 1t raised to the 1 minus 1, which is 1t to the 0. Anything raised to the 0 power is 1. So this is going to be
Interesting. So do we just always use the power rule? And I guess we knock off the constant because I believe the constants don't make it out alive, or I believe they don't well, yeah, we'll see.
0.5 times 1. Now what about the derivative of a constant, like 100? The derivative of any constant is 0.
Okay, it's 0.
If you were to use the power rule, this would be 100, and then times 0, because you need to bring this to the front, and then it's going to be t to the 0 minus 1. 100 times 0, the whole thing is 0.
Okay.
So therefore, the derivative function is going to be a prime of t, which is 0.01 times 2, that's 0.02t, plus 0.5. So this is the derivative. It's going to tell us how fast the amount of water is changing in a tank.
Okay. This is interesting. Huh.
At any time t. So we want to find out how fast it's changing when t is 10. So that's 0.02 times 10 plus 0.5. 0.02 times 10, that's 0.2. And 0.2 plus 0.5, it's 0.7. By 0.7 gallons every minute when t is 10. Now, if we were to graph the original function, this value will represent the slope of the tangent line. How do we know if our answer is correct? Well, one way to determine that is to calculate the slope of the tangent line by approximating it using the slope of the secant line. Now, it's important to understand that the slope of the tangent line represents the instantaneous rate of change. It's the rate of change, the slope of the secant. You can calculate it using 2 points.
Okay, so this is something we've identified earlier. The secant line, the slope of the secant line is the average of 2 points, or the average slope between 2 points. Or I guess the average slope for a portion of the function where the 2 points are on. Or the average slope for the portion of the function between 2 points. That's the best way to say it. Okay, and now we're just talking about approximating it. And then, okay, let's look at this one.
T, which is equal to 0.5t plus 20, where R of t represents the number of gallons of water flowing per minute, and t is the time in minutes. So here's the question. How much water will accumulate in a tank from t equals 20 to t equals 100 minutes? So should we use integration or differentiation?
Okay, this should be integration. This is a definite integration, and not meaning that it's certainly an integration, but that it is not an indefinite one, because we have time t at 20 and time t at 100, and when we do a integration, we're taking an integral at one point and then subtracting it from the integral at one point. So we would be taking the integral at 100 and then subtracting the integral of, or rather, taking the integral, well, how do we say this? So we'd have an integral, we'd input 100, and then that output gets subtracted by the output of the integral at when x is 20, or I guess t in this case.
Remember, derivatives will help you to find the rate at which something is changing. But integration is the process by which you can determine how much something accumulates over time. And so this is an integration problem. Now we can calculate the net change in the volume of water using a definite integral from a to b of the function r of t dt. The difference between a definite integral and an indefinite integral is that a definite integral has the lower limit and the upper limit, and it gives you a number. Whereas the indefinite integral, which is on the bottom, this gives you a function. It doesn't give you a number.
Okay. I think I'd like to capture syntactically what's the difference between syntactically what is the difference and indefinite integral, because I'd like to capture this right here where we have this integral sign b and then a, and then for the other one doesn't have them, and I guess we also have limits, so I'll also put in parentheses i.e. placement of the limits. Perfect.
So make sure you understand that key difference between definite integrals and indefinite integrals. So going back to this problem, to calculate how much water will accumulate in a tank in those 80 minutes, we can see that a is 20, that's the lower limit, b is 100, r of t is 0.5t plus 20.
Yeah.
So let's go ahead and find the antiderivative of 0.5t and 20.
Oh,
So the antiderivative of
whoa, wait.
we can see that a is 20, that's the lower limit. B is 100. R of t is 0.5t
R of t is 0.5t plus 20.
plus 20.
Okay, so we just plug in the function. Okay.
So let's go ahead and find the antiderivative of 0.5t and 20.
Okay.
So the antiderivative of t to the first power is going to be t to the second power divided by 2. Just add 1 to the exponent and then divide by that result. Now for 20, you can imagine 20 as being 20 t to 0. So if you add 1 to 0, you'll get 1 and then divide by that number. And then we're going to evaluate the result from 20 to 100.
Oh, wow. Okay. That's not too bad. Okay. So I think I also need to capture how the power rule. How does the power rule work with integrals?
So the first thing we're going to do is plug in 100. So it's 0.5 times 100 squared divided by 2 plus 20t, or 20 times 100. And then we're going to plug in 20 into this expression. So it's minus 0.5 times 20 squared divided by 2 plus 20 times 20. 100 squared is 10,000, and 10,000 divided by 2 is 5,000. Half of 5,000 is 2,500. And then 20 times 100 is 2,000. Here we have 20 squared. So 20 times 20 is 400. Divided by 2, that's 200. And then half of 200, that's 100. And here we have 20 times 20, which is 400. So now we have 4,500 minus 500. So the net change should be 4,000. So from t equals 20 to t equals 80, the tank will gain 4,000 gallons of water. Earlier in this video, we said that integration is associated with finding the area under the curve. So what we're going to do is we're going to graph this function. This is the y times 20, so we have, let me get a second, we can draw 8. That's our, the calculate the area, and so the final is 11. And the minutes, unit gallon 4, based on this, the height, you're going to by x, a, now 80, 100 angle, that's why, and 20, that's how much in gallon presents in minutes. You just remember when are functions that allow you to calculate the instantaneous rate of change of your change and the slope change. How much by behind those of you, post some links in the description.
Sweet. Wow. Okay. So, like with the power rule, like I can do calculus now, or at least for this simple examples, right? I could do like story problems like that, like right off the bat. So I was really surprised about the nature of integrals and derivatives in that we just kind of grab the integral or derivative of each one according to the power rule, and then we evaluate. So that was actually pretty interesting to me. I think at some point I'd like to derive the power rule, or not derive. Well, yeah, I guess derive. So I'd like to like work through the proof of the power rule, because obviously the power rule is like a rule that has an actual basis, and so I'd like to know the math behind the power rule, because right now it's just shorthand, right? So okay, that's like I'm feeling like really pretty good about this. Yeah, wow, okay, sweet. So I think yeah, geez, like I feel like I'm going to need exposure to what would it like to be, what will be on the test kind of thing. But I'm feeling like pretty good about this. So it's probably the case that there's a lot more that I'm not. Actually, it's certainly the case that there's like a lot more. But for the simple stuff, this is like pretty clear. So sweet. I will see you guys tomorrow. Wait, actually. Oh, what day is it? Wednesday. Okay, this is my last day for streaming for the week, so I'll see you next Monday. Shoot, I may stream again before then. I don't know. Probably not, actually. I'll be out over the weekend. Okay, I'll see you guys.